Welcome, curious minds, to another deep dive. Today, we're getting right down to it, exploring the fundamental building blocks of everything, quarks and leptons.
Yeah, it's a great topic. They sound similar, maybe, but the differences between them, they're absolutely crucial. They really define the universe as we experience it.
Okay, so our mission today is to kind of unpack what really sets them apart.
Exactly. Let's get into what makes a quark and a lepton.
All right, let's dive into quarks first. We hear they're the building blocks of protons and neutrons. But what's maybe the weirdest thing about them?
Oh, definitely confinement. That's the big one. It basically means you just never find a quark all by itself out in the wild, at least not at everyday energies.
Never, so they're always stuck.
Always stuck. They're trapped inside bigger particles. We call them hadrons. Protons and neutrons are those famous examples, making up atomic nuclei.
Trapped. How? What holds them?
It's the strong force, an incredibly powerful force mediated by particles called gluons. Think of it like cosmic superglue.
Gluons, right.
Yeah. And this force has a really strange property. It actually gets stronger if you try to pull the quarks apart.
Wait, stronger. Usually, forces get weaker with distance.
Not this one. Try to separate two quarks, and the energy needed becomes immense. So immense, actually, that the energy converts into mass poof. You create a new quark and antiquark pair out of the vacuum, rather than isolating the original ones.
Wow. So you can't study one alone because trying breaks the rules almost. It creates more instead.
That's a good way to put it. And this confinement, this strong bond, is what keeps atomic nuclei stable, overcoming the fact that all those protons electrically repel each other. Without it, matter, as we know it, just couldn't hold together.
Okay, mind blown already. So beyond being trapped, what else defines them? I know there are different kinds, different flavors.
That's right, 6 flavors. Up, down, charm, strange, top and bottom. They come in 3 pairs, or generations, with increasing mass.
Up and down being the common ones in protons and neutrons.
Exactly. But what's really unique, property-wise, are 2 things. First, their fractional electric charge, not like the electron's simple minus 1 charge. Quarks have charges like plus 23 or negative 13.
Fractional charge. Okay. And the second thing?
Something called color charge, and this is key.
Color. Like red, green, blue quarks, are they actually colored?
No, not visually. It's just a label for a quantum property. Think of it like positive and negative electric charge. But for the strong force, there are 3 types, red, green, and blue, and they're anticolors.
Okay, so it's a type of charge needed for the strong force.
Precisely. Only combinations that are colorless or white, like having 1 red, 1 green, and 1 blue quark together in a proton, or a color and its anticolor in another type of particle called a meson. Only those combinations can exist as part of a stable hadron. This color charge is why quarks feel the strong force, and they feel the other forces too. Weak electromagnetic gravity, all 4.
Got it. So, quarks, confined, fractional charge, color charge, feel the strong force. Now let's switch gears to leptons. The electron is the famous one, right? How do they differ?
The electron is definitely the poster child. And the biggest difference is staring us right in the face. Leptons do not feel the strong force. 0 interaction.
Ah, okay. And why not?
Because they don't have color charge. Simple as that. No color charge, no talking to gluons, no strong force interaction.
So that means they can be alone.
Exactly. They can exist freely, isolated, like the electron orbiting an atom. Besides the electron, the lepton family includes the heavier muon and the tauon. They all have that Ni1 charge. And then there are their partners, the neutrinos.
The really elusive ones.
3 types here, too. Electron neutrino, muon neutrino, tau neutrino. They have 0 electric charge, very tiny mass, and interact very, very weakly. And just like quarks, leptons also fall into 3 generations.
So 3 generations for both families, but the key split is that strong force interaction driven by color charge.
That's the absolute core distinction. Leptons ignore the strong force completely. They do interact via the weak force, gravity, and if they have electric charge like the electron, the electromagnetic force.
So their roles are fundamentally different then.
Totally. Quarks build the heavy, stable cores of atoms, the nuclei, thanks to that powerful, strong force grip. Leptons, like the electron, are generally lighter, they're free agents, and they're crucial for things like chemistry, how atoms bond and interact.
Okay, we've really nailed the differences, but is there anything fundamental they actually have in common?
Yes, there is. And it's incredibly important. Both quarks and leptons are fermions.
Fermions, okay, what does that mean for them?
It means they obey a fundamental rule called the Pauli exclusion principle.
Pauli exclusion. I remember that from chemistry. It's why electrons fill up shells in atoms, right? They can't all just pile into the same state.
Precisely. That's the most familiar consequence. The principle states that no two identical fermions can occupy the exact same quantum state at the same time. It's like they're fundamentally individualistic.
And this applies to both quarks and leptons.
Yes. It's what gives matter its structure, its volume. It prevents everything from just collapsing in on itself. Think about it. It operates from the scale of electron orbitals in an atom, all the way up to cosmic scales, like preventing neutron stars from collapsing further under gravity. It's nature saying no crowding for these fundamental particles.
Wow. So different interactions, different properties, but united by this deep quantum rule. Confinement versus freedom, strong force versus no strong force, but all obeying Pauli.
It paints a really interesting picture, doesn't it? And there's one more thing that always comes up here, kind of a mystery hanging over all this.
No, what's that?
Those three generations we mentioned, for both quarks and leptons.
Right, up, down, and the electron are generation one, then charm strange, and the muon,
Yeah.
top, bottom, and the tau.
Exactly. And each generation is heavier and more unstable than the last. But all the stable matter we see around us, everything that makes up you, me, planets, stars, it's almost entirely built from just that first generation. Up quarks, down quarks, electrons.
Yeah, that's true. The other particles are mostly seen in high-energy collisions, right? They decay quickly.
Right. So the big question is, why? Why are there three generations? Why did nature make these heavier, unstable copies if they don't seem needed for, well, for stable stuff?
Huh. I never really thought about why there are three.
Nobody knows for sure why three, not two, not four. This repeating pattern feels like it should mean something deeper, maybe hinting at some underlying structure or theory we haven't discovered yet. It's one of those tantalizing, open questions in physics.
A fantastic puzzle to leave us with. Even in the most fundamental building blocks, there are still these deep mysteries about why things are the way they are. Lots still to explore.